Hello students, in this video we are going to study how we can find out the principal and shear stresses which are occur on the both side, that is on the upstream or downstream side of a gravity dam. Principal stresses, it is nothing but a stress that is having a intensity which acts in a perpendicular direction, because the water pressure acts on it in the perpendicular direction only, with the no shear stresses. So the principal planes are mutually right angles to the face of the water. So let's discuss. See, consider the for finding out these principal stresses, we have to consider or we have to draw a diagram, or we have to zoom the part of the toe section of a gravity dam. Okay, so on the downstream side of a part, that part we are going to consider. So you can see this image here. We are considering, see, you can see A to C. AC is the face of a dam on the downstream side, and from A to B we are going to connect, and we are going to draw one straight line, and it joins on the base width of a gravity dam, so that one triangle is formed. And by zooming out this triangle, or by working on this triangle, we can find out, we can derive the principal stresses equation as well as the shear stresses equation. See, these stresses are very much important. How and at what rate the shear stresses will develop on the hill or on the toe section, that being a civil engineer, being a water resource engineer, we have to study, or we have to analyze this. If we don't consider these stresses, so what happen, certainly the gravity dam will definitely fail in upcoming days or in a short period. So you can see here there is a triangle ABC. AC is the face of the triangle on the downstream side. This part is denoted, and the length of this AC is considered as a DS. You can see the BC is taken as a DY, and AB is nothing but a DR. So the stresses acting on this faces are mutually right angle to this. So here you can see, while finding out the stresses and finding out the intensity of a stress, we have to multiply the force into a distance. So on the AB part, sigma 1, that is principal force is acting on this part. On the AC part, P, that is a water pressure which is actually available on the downstream side, which is termed as a tailwater. So this water pressure will act on the AC part. So this force will be denoted by a small p. So p into ds, this is the intensity of a stress. And here you can see the pn into dy on the base width, that is on the bc side. So pn is nothing but a normal stress. In the previous slide, in previous video, we had studied how we can find out the normal stresses in a mode of a failure, that is while we consider the, or while we dealing with the compression and crushing zone. So for finding out, or to keep the gravity dam in a stable condition in compression zone, so we have to check the normal stresses, and we have to find out the normal stresses. So here the force of a normal multiplied by the distance of this base width, or distance of this BC. So Pn into dy gives us the intensity of a pressure that is acting on the BC side. And you can see the tau shear stress is acting in the opposite direction. Yes, we know that the friction is always acts in the opposite direction to the direction of a force. So the tau is also showing here, and this is a triangle. So here the A has a triangle 90-degree. So this is a uh, theta, or we can say the angle of a. Then here B, phi, this is denoted by the phi, and C with the horizontal distance of the gravity dam, we got the theta on the downstream side. So this is principal stresses, and we can say by analyzing this diagram, we can find out the shear stresses also. So let's start. See, principal stresses. Consider an elementary triangular section at either on the hill or on the toe of the dam section, such that the stress intensities may be assumed to be uniform on its faces. So you can consider this triangular section on either on the hill or either on the toe section. So then the face of the dam will be a principal plane, as water pressure acts on it in the perpendicular direction with no accompanying shear stress. Since the principal planes are mutually at right angles, the plane AB, see, the plane AB considered at the right angles to the face AC. Okay, then it will also have only a normal stress on it and will be the other principal plane. The forces acting on these elementary sections are, how many forces are acting on this? Let's discuss. For this, just we had considered that let ds, dr and dy be the lengths of AC, AB and BC respectively. Then P, you can see here, P is the intensity of a water pressure acting normal to the face of the dam. Then we have a sigma 1, that is principal stress on the plane AB. Tau is the shear stress on the plane BC, and Pn, that is normal stress on the plane BC. So considering, obviously while designing the gravity dam, we are always considering that or we are always designing this gravity dam with respect to the unit length of the dam. So considering the unit length of the dam, the normal forces on the planes AB, BC and CA. See, you can see AB, BC and CA. So the normal forces are respectively sigma 1 into dr. Sigma 1 is the principal stress acting on the AB. So forces multiplied by the distance gives us the normal intensity of a force which is acts on the respective side, respective face of the dam. So sigma 1 dr, then Pn dy which acts on the BC, and P into ds which acts on the CA part. So if we resolve all these forces in the vertical direction, so we get in the vertical direction. So how many forces are or acts in a vertical direction? So only one force is there, that is a a normal force into a dy which acts on the PC part. So Pn dy, which is equal to the, now if we resolve these two forces which acts on a AB and acts on a AC, so it has two components. One is a vertical, one is a horizontal with respect to the sine, with respect to the cos. So here if we resolve this part, so we will also get a vertical force acts on the AB or as well as acts on a CA. So P and dy is equal to the, here we had found out, yes, P and dy is equal to the P, that is pressure, water pressure, into ds sine phi plus sigma 1 dr cos phi. Okay, when we resolve all these forces or these intensities in two direction, vertical and horizontal, and if we resolving all these forces in a vertical direction, we got this value. By then arranging all the terms, we can find out the d, that is, but we know that dr, it is equal to dy cos phi. See, dr here, dr is nothing but dy cos phi. How? See, cos phi is nothing but, or cos theta, it is equal to the adjacent side to the hypotenuse. So if I'm using, or I want to find out the cos phi in between the AB and BC part. So here, if I applied the cos phi, so adjacent side cos phi, it is equal to the adjacent side is the dr, and hypotenuse is nothing but a dy. So dr is equal to the dy cos phi. Similarly, here also ds is equal to the dy sin phi. Sin phi, if I want to find out the relation between this ds and dy, so I am simply using the sin phi equation here. So sin phi is nothing but a opposite side to the hypotenuse. So here also opposite side is the sin phi, opposite side is the ds, and hypotenuse, that is which has the face in opposite to the 90-degree straight line. So it is a PC line and it is a dy line. So ds is equal to the dy sin phi. Again, Pn, so rearrange this term. So we will get, see here, Pn dy. So we know that dr is equal to dy cos phi. So simply, and ds is equal to dy sin phi. So can we substitute this value in above equation? So we will get P into ds is nothing but a dy sin phi. So I am simply substituting this value here. So dy sin squared phi plus sigma 1 into dr is nothing but a dy cos phi. So dy cos squared phi. So again, if we rearrange all the terms, so Pn is equal to, here dy is similar or same value, so we can easily scratch out that dy. Then we get that Pn is equal to P sin square phi plus sigma 1 into cos square phi. Then after scratching out the similar terms from each and every phase, that is gy, we are going to scratch out. Then again rearrange this term. So we will get sigma 1 is equal to the Pn minus P sin square phi upon cos square phi. Or sigma 1 is nothing but a principal stress, and our main agenda is to find out the principal stresses. So sigma 1, it is nothing but a Pn, see, 1 upon cos square is nothing but a sec square phi. So simply we can use here 1 upon cos square, that is sec square phi, minus P sin square upon cos square is nothing but a tan square. So simply we are substituting and we are modifying this equation as a sigma 1 is equal to Pn sec square phi minus P tan square phi. And this equation is the principal stress relationship and is applicable to both upstream and downstream phases. Remember, this equation is applicable on the hill as well as on the toe section. Now, however, for the downstream side, that is on the toe section, the worst condition will be when there is a no tailwater. So hence P will be 0. So if tailwater is not available on the downstream section, so simply the P will be 0. So in that circumstances, the principal stresses, so here the principal stresses will, the formula or equation of the principal stresses will again change, that if there is a no tailwater, so here P will be 0, only Pn into sec square phi will arise, or will be the equation for finding out the principal stresses on the toe. So likewise, if there are certain conditions are there, so if sometimes the hydrodynamic pressure due to the earthquake will arises and will occur on the downstream side, that is on the toe part, so the equation becomes sigma 1 is equal to Pn sec square phi. See, the first part does not change at all. Okay, Pn, that is a normal stress. We have to find out, or we should find out, the normal stresses which occurred on the toe or which occurred on the hill for finding out the compression and tension zone on the both the side. So Pn sec square phi minus P. P is nothing but the water pressure of a tailwater or tailwater which actually available on the downstream side, minus PE is a hydrodynamic water pressure due to the earthquake into tan square phi. So similarly, this if the earthquake, and because of the earthquake, hydrodynamic pressure will taken into consideration, then principal stresses on the upstream side, that is on the hill side, will also occur, and equation becomes sigma 1 Pn sec square phi minus P, that is water pressure on the upstream side, plus PE hydrodynamic water pressure into tan square phi. So this is the equation which is arises on the, or which is used for finding out the principal stresses on the hill on the upstream side. And one should be noted that for the upstream phase, sigma 1 will always be less than P. Sigma 1, that is principal stresses, will always be less than the water pressure P, and hence sigma 1 is the minor principal stress and P is the major principal stress for upstream phase. Obviously, water pressure or the pressure due to the water which is stored on the upstream side, it's in a major zone and it is in a major part. Hence, this water pressure is the major principal stresses, and the sigma 1, the principal stresses which occur on this phase or on this side, upstream side, is the minor principal stress. So always the sigma 1 will be less than the water pressure on the upstream side. And again, also if upstream phase of the dam is vertical, upstream face of the dam is vertical, then the obviously there is no angle, there is a no slope, so simply the phi will becomes 0, and sigma 1, it is simply equal to the normal stresses. Okay, so this is how we can find out the principal stresses on the toe as well as on the hill, and depending upon the by occurring or by considering various types of forces, we can use a various equation, or we can adopt various equation for finding out the principal stresses on hill or on the toe. Likewise, here you in the diagram you are seeing that there is a tau or there is a shear stress which occur on the base width of a dam, which is in the opposite direction of the force. See, let me see you in this diagram. Let me show you that this tau is nothing but a shear stress which acting in the opposite direction. Our force of the direction is in the C direction, C towards the point C, and shear stress is always acts in the opposite direction. So how we can find out this? So for finding out the principal stresses, we resolve all these forces in the vertical direction. Now for finding out the shear stresses, we have to resolve in these forces in the horizontal direction. So how many forces are there in the diagram which has the direction horizontal? So only the shear stress which acts in the horizontal direction and which acts with respect to the dy, with respect to the BC length. So here tau into dy, that is tau multiplied by dy, distance of the or face of the dam, that is dy, is equal to, when again as I had told you in principal stresses also, for finding out the vertical and horizontal component, we have to resolve these forces which acts on the AB and which on the CA face of the dam. So here also for finding out the horizontal forces, we have to resolve this into a horizontal part also. So here we will get the value as a sigma 1 dr sine phi minus P ds cos phi after resolving this into a horizontal direction. So let's rearrange the term. So tau is equal to sigma 1 sine phi. So simply we can shift this dy into or towards the right hand side. So dy will be divided or will taken into a division. So sigma 1 sine phi dr upon dy minus p into ds upon dy cos phi. So here we will get the value, or if we rearrange that term, so tau is equal to sigma 1 minus p. So just side out that part, sigma 1 minus p. So the left out part is sine phi dr upon dy and ds upon dy cos phi. So after rearranging all the term, we will get the value as tau is equal to sigma 1 minus p cos phi multiplied by sine. So substitute the value of sigma 1, which has been derived in the principal stresses equation. So sigma 1 is nothing but Pn sec square phi minus P sec square Pn sec square phi. This is the value of a sigma 1 on the toe section. So simply substitute this value. So we will get Pn sec square phi minus P sec square phi bracket complete cos phi sin phi. Or again, if we rearrange that term, so sec square will get cancelled, or if simply we can taken out from the bracket section, so tau is equal to Pn minus P tan phi. So the above equation is applicable for downstream side only. This is applicable on the toe section only. For the upstream side, the magnitude of a tau will be the same as that will be given in the equation, that is equation which is equal to tau Pn minus P tan phi, but its direction will be reversed. Is the direction will be reversed. So here simply for the upstream side, the equation becomes tau is equal to minus c, because of the reverse direction here. The only the minus sign will be added, minus into bracket Pn minus P into tan phi. So this is the equation for finding out the shear stresses on the upstream side. And if the tailwater is neglected, if we don't consider the tailwater, then the shear stress on the downstream side will be tau is equal to simply a Pn into tan phi. And if the hydrodynamic pressure due to the earthquake will be considered on the downstream side, then the equation becomes tau is equal to Pn minus into bracket P minus Pe bracket complete into tan phi. Similarly, the shear stress for the upstream side, when there is a hydrodynamic pressure due to the earthquake is occurred, so tau is c. Whenever we are considering the shear stress on the hill part, on the upstream part, then we have to reverse the, or we have to give the minus sign on the upstream side, because the shear stress direction will be reversed one. So here all the values that we are going to calculate, this value is will be in a minus or will be in a negative zone. So the tau is equal to minus bracket Pn minus in the bracket P plus Pe bracket complete into tan phi. And if the upstream section is vertical on the upstream side or on the hill section, then phi is equal to 0 and tau is also 0. So this in this manner we can find out the shear stresses as well as the principal stresses. See here there is a certain mistake in the equation in this slide. Here on in the last line, that is for the upstream, the tau is equal to minus, see don't forget, minus bracket complete Pn minus P into tan phi. See there is a mistake of editing part. So just look out that equation, and whenever the conditions are given, so according to this condition, we can find out the principal stresses and shear stresses on the gravity dam. Thanks for watching this video.